Super. Well, thanks all for coming. My name is Alec Peterson. I'm Chief Technology Officer at Message Systems. And I'm going to talk to you guys today about messaging at scale. So I'm just going to go in a little bit about what the messaging world looks like, because I know that for especially following Archer's talk, the messaging world is a little bit different from the web world, to just kind of paint the picture, and then want to talk about some of the challenges that we've run into in the 15 years that we've been doing this. So the digital messaging landscape can largely be thought of as being made up of senders and receivers. So on the send, and some fall into both categories. On the sending side, you have web properties that a lot of you all likely represent. You have person-to-person communication, so you send a message from one person to another. Those aren't necessarily entities in and of themselves, but may well be subscribers with a per se receiver of some sort, which we'll talk about in a minute. And ESPs. ESPs in the market, for those of you who aren't familiar, are basically companies that more traditional organizations and brick and mortars and such may outsource their messaging to. And these are the largest senders of messages. On the receiver side, you have more traditional mailbox providers. You have Yahoo, Hotmail, Gmail, and along those lines. You have MSOs, which is the industry term for cable carriers that like Comcast and Cablevision and so forth, and they provide mailboxes for their subscribers. And telcos, so you have more traditional telephone companies like Verizon and AT&T and so forth. So the volume of messaging that's moving is largely going from the traditional senders to the traditional receivers. And then the receivers send a significantly smaller amount of that mail back. So when I talked about the person-to-person messages and things like that, that's generally a much smaller volume than what traditionally gets into the larger commercial messaging. We won't get into the discussion of what spam is and isn't, because that's different from everybody else's from every person's perspective. This also doesn't really factor in abuse. This is the expected legitimate stream of messages. So amongst all those messages, our software is touching 20% of those legitimate messages. So just to give you a sense of where we sit in that market, these are the kinds of problems that we've solved dealing with this volume. So enough of that. What does it take to drive modern digital messaging? Well, from a fundamental standpoint, it's not particularly different from what it takes to drive anything else. Large amounts of server horsepower. There's a lot of computations going on to take care of all the tasks that we're going to talk about. Fast disks, and I realize disks is becoming a somewhat nebulous term with solid-state disks and various other technologies that people are using, but fast disks are necessary, and incredible amounts of bandwidth, because ultimately the bits have to go from A to B. Now, there are a lot of areas where messaging diverges. One of the most important ones is that you guys, when one is working at a web service provider of some sort, you think about your carrier relations oftentimes in terms of your carriers, who you buy your bandwidth from and so forth. But as far as the other end of that transaction, there's usually not a huge amount of thought that goes into that. But when you're sending messages to these carriers, the carrier relations aspect of this is incredibly important. And in some aspects, that's a technology problem. But in many aspects, that's really almost a business or a political problem. So, making sure that when you are dealing with messaging, keeping in mind that sort of relationship on a macro basis is actually incredibly important. From a technical perspective, one of the most unique things is the fact that messaging traffic, in terms of sending messaging, it's a push activity. Right? When you're sending web traffic, it's a pull activity. You have a client pulling something out from you. But with messaging, it's all push. So that brings in a whole variety of challenges that we'll get into in terms of directory lookups, various queuing challenges, and things of that nature. So philosophically, messaging is a means to an end, right? It's an indispensable tool. You use it all the time, every day, for all sorts of things, just to talk to your friends, to interact with various applications that you use. But ultimately, it exists in support of a larger application, of a larger business application. So when you're looking at companies that have done this really successfully, Salesforce is a great example. They were one of the first companies to really embrace message-driven workflow. So they will, so the Salesforce CRM platform, you have salespeople out in the field and various people working for a company who will get emails about a deal, about an opportunity, about a case. They can get those emails, they can reply to them and interact with the Salesforce system over email. Facebook's another great example. You get your Facebook notification over email. You can hop into the Facebook app and do something, or if you just want to, reply an LOL and send, you can, or a me too from back in the AOL days, you can do that too. Match.com has similarly done that. Match is the matchmaking service. One of the most important things about Match is early on when you're meeting somebody, you might not want them to actually have your real email address. That's how a lot of bad things start. So, or good, it can go either way. But they embraced that, right? They said, okay, that's okay. So they have they do double-blind emails. So you could they could do that through their portal, but people often felt more comfortable. Match is one of our customers. Talking with them, people felt more comfortable just typing something in an email instead of going into the Match portal and doing that. You could do that too. But being able to do it through email, the email would go into a special address at Match and then get routed double-blind back to the sender. Then when they both agreed, they could get in touch, get married, and get divorced and fight over it and all that. But that wasn't their problem. But this is where we've come. I mean, email has existed for decades now. I mean, I think this morning we're talking about standards. The email standards started, I think in the 70s. So we're well over we're into the 40th year of email now. So the technologies have evolved. Sadly, the standards may not have evolved as much as some of us would have liked, but again, that's a separate discussion. So when we built our products, this really started as a consulting project. It was actually an OmniTI consulting project of all things. But what we did was we were working with a company that at the time was one of the larger senders of bulk legitimate email. It was an online lottery provider. So they had people that would sign up, they'd watch ads, and they'd get their emails about that. And they wanted to get these. Like this was and still is a real business. There are a lot of other competitors now, but these guys were one of the first. And one of the things that they needed to do was they needed to get these emails out. So this is before the days of really in-depth spam filtering and things like that. You had some very rudimentary controls, but more than anything, you just had a volume problem. The carriers were just not up to the task of receiving these volumes of email. The carrier relations I spoke about earlier, there wasn't really the notion of formal email carrier relations contacts on the carrier side, which created a problem because when a sender had something that said, look, I want to figure out how to work with you guys, there wasn't even anybody to talk to. But the bigger problem was that the software available really made it very difficult to get that information. Also, it just took a lot of servers. So our first task was to figure out what can we do to make things better. So I'm going to go through a basic flow of where we came from. This is kind of the standard, pick one, XIM, postfix, QMail, sendmail. The structure of these is basically the same. It's a process and disk-based message flow. So in a system such as this, you have your queue on disk, and then you'd have a persistent queue runner process. When a new connection comes in, good, you can read that. When a new connection comes in, that creates a new SMTP server process. Fair enough. So that message is received, and there is both a directory write and a message write. So you're writing message data and you're creating files on disk into the disk queue. Fair enough. Then to deliver that message, the queue runner process reads the directory to find the messages and reads the message details and says, okay, I have to deliver that message. Fair enough, no problem. Then the delivery process is spun up to actually do the delivery. That needs to read the message from the directory and the actual message body, and then do a directory write in the form of actually deleting the message from disk once it's delivered. And then all of that activity happens there. Seems pretty simple, right? Well, things start to get a little complicated when you start trying to multiply that out, and that's exactly what that looks like, and that's exactly what happens. So the challenges is, aside from the fact that, the second bullet here, all the processes being created, the disk is the only source for data in the queue. So every time you wanted to do any sort of queue introspection, you needed to actually traverse the entire queue. And that meant walking through the directory. Probably everybody here has run an email server themselves at one time or another. You have a queue of 50 or 100 messages, no big deal. These things would start to fall over at 50 or 100,000 messages. And not just because of that volume of messages, because when you're trying to look at the queue, you're also doing all the reception and all the delivery at the same time. So there's this constant struggle for access to these resources. And more often than not, you'd be able to create messages faster than you could deliver messages. So, it would just be this vicious cycle of just the system bleeding to death, basically. And then, Unix processes are generally created for reception and delivery on demand. There are some optimizations that have been put into those to reuse connections for certain things, but the fact that separate processes were required to do all of that was a significant bottleneck just because it used up a huge amount of resources. And DNS information was also cached externally. So the first thing that we did was we came up with a new structure for handling the network events. So we went with a hybrid thread and event loop structure. So we created an event loop abstraction layer using the OS-specific I/O multiplexers. I might, if there's still room, I might do a lightning talk on why select and poll suck, but I think everybody already knows that. If anybody doesn't, we can talk about that. Implement all the network state machines as non-blocking reentrant event handlers. So implement them all in terms of always doing non-blocking I/O. When you need to do blocking I/O, think of actual disk writes, or think of opaque libraries like an LDAP lookup or a database lookup or something like that, where you don't have visibility into the state machine to make it non-blocking. Push that off to a separate thread pool, and then all data. But then the key is, all data passed between threads is done using common address space, because all these are running in the same address space. So you don't have to do any sort of expensive passing through the disk. So what this is accomplishing is you had those separate processes, and they were all communicating through the disk, which is not cheap. Now they're communicating, within memory for free. Now we're not using 768 gigabytes of memory, so that is actually cheap. And when we get to that level, we'll deal with that problem. But anyway, the notion of the event loop and thread pool architecture is pretty simple. Every session, be it a delivery session, an inbound session, whatever, is represented as an event in the event loop. So when that event loop needs to do something that's blocking, it's just popped out of the event loop and pushed down into a thread pool. And then same thing with another one, and they can be moved to task-specific thread pools. The thread pools are persistent, so the threads are persistent. They live for the life of the invocation of the process. So we're not spinning up and tearing down threads, which further saves us a huge amount of effort, especially when you consider that many of our operations are short. Like we're doing, disk writes and things like that take, for good disks, it takes less than a millisecond. So spinning up a whole thread for that would be a shame. So being able to leverage persistent threads is a really key aspect of what we're able to do. And then when the job is done, the thread pool pushes it back into the event loop, and off it goes. So that gets us able to handle really quick network state machines and deliver stuff quickly, but we've still got the problem of the queue. So first, a word about RFC 5321, which is the successor to RFC 2821, which was a successor to RFC 821. It's the SMTP RFC. That's all it is. Section 4.1.1.4 explicitly requires messages to be written to disk prior to acceptance. The reason for that is that when a system accepts responsibility for a message, it is basically telling the sending system, I got this. Because when that happens, the sending system needs to delete that message from disk. Now, because of the fact that SMTP is not a three-phase commit type protocol, there is a window of time even following this where you could have duplicated messages. But the important thing is with this protocol, you can never have missing messages, and that's the real thing you want to avoid. So the messages must be written to disk, so we have to have that. That just is the protocol, and we can't get around that. But the interaction with the disk can be minimized. So maintaining an in-memory snapshot of the queue, we'll talk about the data structures we use there to do that. only write the message to disk on reception and unlink it on delivery. So the fast path through the system means that we touch the disk to write it and we never read the disk, which is a huge win. Because also with the fact that we're able to deliver so quickly, a lot of times we can actually write the message to disk and unlink it before it ever even gets written to the disk. It's still fumbling around in the buffer cache somewhere. So we can get some huge efficiencies that way. And we do get some huge efficiencies that way. And then also be smart about what's kept in memory. The key thing to remember about that is, you have a finite amount of memory, so you want to cache as much as possible, but then you have to be smart about paging it out. And we've definitely suffered some lessons there of not being smart enough. We actually had a problem once where the system would get into this loop where the messages that were in memory were all the delayed messages, the message we wanted to deliver later. So all the new messages coming in all had to go through the disk because all these messages were sitting off in the queue. They weren't in a place where we could actually get at them and say, no, we don't need them anymore. So those kinds of being smart about what messages are kept in memory and being able to update that on a regular basis is really important. So this was a really fun one. Representing the queue on disk. Seems like a simple operation, right? You write some files on disk, you have a message ID format so that you can learn some information about them, not a big deal. As we said, it has to be on disk, so we've already agreed to that. But arranging them on disk is really important. The kernel and buffer caching significantly affects this performance. We notice when we have a queue of a few million messages and we need to traverse the entire directory structure, we can have our startup times vary by like a factor of 100. Like we start up the system when it hasn't traversed the queue in a while, it can take like 2 minutes to start up. And then we start it up again right after that, it's up in 5 seconds. So that taking as much advantage of that caching as possible really impacts your performance. Directory size is something that we didn't think was going to be important in the way that it proved to be very important. So the size of the directory, I'm just talking about fundamentally the number of entries in the directory, which results in the directory structure size. So here's a little flow chart. More files on disk, larger directory structure, right? So the larger directory structure means you start having degrading performance because, well, it's more to do. That makes sense, right? All right, so fine. We deliver some messages. We remove files from disk. So the directory coalesces, right? Wrong. It actually does not do that. And that is one of the more frustrating experiences we had. Now, granted, 90% of this experience was on ext2 and ext3 on Linux, but we did a bunch of testing with DFS and Solaris? No. UFS. And UFS had the same problem. And it's a hard problem to solve, right? You have a bunch of files sparsely populated throughout the directory. Coalescing that is an expensive operation. It's hard for the OS to know when to do that. But the problem that we had was that we had a structure where we had 256 directories for our messages, and those directories lived forever, right? So we get a bolus of 5 million messages and deliver them out, but the directory search times would still be through the roof. And the only way we could, even when we completely deleted the contents of the directories, but not the directory structures themselves, meaning we delivered all the messages, this directory still remained huge. It was so vexing because times we get in this position and we just say, well, stop the system, delete, move this out, do this, recreate these directories. It was just such an ugly process. But then we realized, hey, we're delivering messages here. We're moving forward in time by definition. So we went with a structure of time windowed directories. So what we do is, for every hour that the system is online, there we go, we create a directory. And then that structure of 256 directories we had in our master spool now gets mirrored in each one of these directories. So then, once we deliver all of the messages from January 1st, 1970 at midnight, those directories are gone. But if we have some from 1 o'clock to 2 o'clock, that sticks around, but then the one from 3 o'clock is gone, and so forth. So the worst that we have is a temporary condition where a major volume of messages, which can only ever be an hour's worth of messages anyway, causes the system to slow down, but then that whole thing just rectifies itself. And there we go. So now talking about that was the queue on disk. Now we talk about, okay, we've got the queue on disk, but remember, we want to hit the disk less. We're only going to, we're not going to read the messages off disk, so we need to have a data structure in memory to drive our behavior. And we are going to hit that data structure a lot. Like, we're going to be all over that. So looking at how to design it's really important. So the attributes of a message queue generally are, when you're doing an on queue, meaning you're pushing a message in, it requires a specific position in the queue. So when it's a brand new message, it usually just goes at the end. But remember, with a message delivery system, you'll have retries. So when you have a retry, that gets scheduled at a particular point in time. So you need to be able to find that and put it in that spot at the given point. But the dequeue operation, which is actually a lot more common than you'd think, because not only are you dequeuing, but you're peeking at the head of the queue to figure out what you need to do. The dequeue operation actually happens a ton. So optimizing for that dequeue operation is really important. And the other thing is the recipient domains vary significantly in terms of volume as well as how fast they'll accept messages. On the global net, probably well over 90% of the mail goes to about 100 domains. And then the other 10% goes to about 300,000 domains. So it's a very bipolar distribution, and it tails off really fast. Like, it's that 90%, and it's not even like the next 100 is like 2%. That next 100 is like 0.1%, and it just really, really tails off quickly. So leveraging the in-memory queue is key because it allows us to. I already said much of this, so right. I already said all that. Moving on. So I actually come from the networking world. Who here remembers May East, like the exchange point? Who here remembers the head-of-line blocking problems in May East? Awesome. So May East back in the 90s was one of the primary internet exchange points. Back before the days of private interconnects, you had these big FIDI switches, 100 megabits per second. They were fast. And they were FIDI switches. They were made by DEC. It was called a FIDI DEC gigaswitch, and that was really the state-of-the-art technology for moving that volume of traffic. And I was doing some research for this project and looking into head-of-line blocking. I actually found a white paper by the guys who designed the gigaswitch talking about this exact problem, head-of-line blocking. So the problem is this: when you have a single queue. And you can have multiple queues in a system, but just think about a single queue for the sake of simplicity. And you have each one of these different colors. Sorry for those of you who are colorblind. Represents a different destination domain. So if you look at this now, all 4 of these domains, see for the top 4 are ready to accept a message. But the blue one, see the blue one here, the one that's at the front of the queue, is not ready to go, right? So this guy here is blocking the delivery to all of these guys that are thumbs up, good to go. So that's what's called head-of-line blocking, because you have something at the head of the line that's blocking other stuff. So when that guy is good to go, then everything can get delivered. So the interesting thing is that the DEC white paper talks about the solution to head-of-line blocking, which is virtual queues. But they said that they modeled the traffic that was going to be happening at the exchange points and decided they didn't need to do it. And then 2 years later, they had to go and do it. So I didn't actually know that history, that they'd actually said they didn't need to do it, and then they had to do it. But it was funny to see the guys talking about the gigaswitch, designing it, and saying, yeah, we know it's going to be a problem, but it's not really going to be a problem. It was a problem. So the solution there is virtual queues. So in the gigaswitch place, it was a per port thing, because what happened is each port on the gigaswitch had an output queue. Right? So that queue that I was talking about back here, this is basically an individual queue, and then it would come on. I'm too clever with my animations. So that one queue would cause would cause everything else to back up. So the notion of virtual queues creates a separate queue for every destination port, or in our case, every destination domain. So then, as a.com is good to go, its messages go out, and the fact that the other domains are blocked is fine. So then the other domains just do their thing as they're able. So this was actually a problem for a lot of the older MTAs as well, in differing ways, but it related fundamentally to the same problem, that you had slower deliveries, slowing things down that could be going a lot faster. So we went one step further, though. Because at the end of the day, delivering, messaging systems, MTAs don't generally just deliver one type of message, right? You have messages that are more important than others, messages that are, you might have a transactional message versus some sort of bulk message that isn't quite as important or in a volume. So you need to be able to have different delivery scopes to take that into account. So we've created this notion of delivery scopes within the system so that you can assign messages to individual scopes. So what this means is that within each of those scopes, you have a queue for every destination domain. So you could have, for example, all of the messages to a.com are good to go, so they all go out of all the scopes. But then you could say, scope 3 is super fast, so it's able to get all of its messages out, and scopes 1 and 2 then get them out as they're able to. So it's incredibly powerful. And those of you who've done the math, yes, that ends up being potentially millions and millions and millions of queues. And that is the problem that we solved. But with that power, that really gave us the ability to do some pretty remarkable delivery structures. So DNS. Everybody loves to hate DNS, but it's absolutely necessary. So again, when you're on a system that's really doing more pull activity, that's serving pull requests, the DNS you might need to do some reverse DNS queries, talk to some of your customers, but you're generally not doing a really large volume of DNS. But doing the math here, remember I said 300,000 domains. Each domain could have 1 to 13 MX records. Each MX record could have 1 to 13 A records, and then many domains try to get clever with TTLs. So what we did is we implemented a caching asynchronous DNS server DNS client, as part of our event loop infrastructure. So basically, it's just another one of those events that sits in that event loop I was discussing earlier. Caching that DNS is key. Every time you use the DNS, you don't want to re-query it. But honor the TTL, but be reasonable. 5-second TTL on your mail server, come on, like that's ridiculous. A 1-year TTL, probably not a good idea either. So we early on we realized this, and by putting in a floor of say 60-second TTL, which even for a mail server is still kind of low, we were able to reduce the volume of DNS queries we'd send out by like a factor of 10. There are just a lot of people out there trying to be clever with the DNS. And thinking back to that event loop structure, we have one DNS event, but it's all running asynchronously on that UDP socket, so it can have 65,000 active queries going on at once. It can beat the crap out of DNS. So it's not that we can't do the DNS queries, it's that the DNS infrastructure supporting it doesn't like that so much. We used an existing library. So back in the day, we used libarez. It's all part of the old Project Athena. libunbound, we looked at, it's been really interesting. We haven't had reason to go that direction, but it's something that that for anybody looking for doing something like that, it looks very promising. I wouldn't use libarez. It's ancient, hasn't been touched in years. Also, be careful with edge conditions. Various impossible replies and things that can't happen somehow always find a way to happen in DNS. That's just the nature of the beast. Also, watch out for the ever-present Microsoft hack of allowing IP addresses as MX records. Every DNS server I've looked at, except the Microsoft NT Windows 8 whatever server, allowed you to actually define IP addresses as MX records, which is 100% illegal. But I need to do it, so yeah, that one's frustrating. Yeah. So with all this stuff, that's our first pass. So now we've got the Unix processes not being created frequently. We've significantly reduced the disk usage while significantly increasing our performance. And the DNS activity is now being done in a sane manner so that from a fundamental functionality perspective, we have an incredibly high performance system that allows us to get real-time views into the queue, because that queue data structure I was talking about earlier, you can look directly at that whenever you want and get a very clear view of what's happening in your system. So now that we've gotten to that point, now it's time to go to the next step, right? We're getting messages out quickly. We got a view into the queue. But the message disposition data, what happens to the messages, isn't really being processed properly. We didn't even worry about that before in the previous system because we just knew that we were losing a ton of messages. And what was happening with them, we were just so focused on getting them out that doing any sort of more detailed and strategic operation around message dispositions just wasn't really as important. But now we can actually focus on that. And the other thing is that, again, the message generation process is largely isolated within the application. The application has way too much intelligence about what it takes to put together a message and talk to the messaging environment and things like that. So looking at a typical outbound message flow in an internet environment. Wow, I made that too small. That says fully formed message injection. I can barely even read it on my screen. So the fully formed message injection goes into the MTA, and then the message delivery goes into the carrier. The carrier will send the message disposition back to the MTA, which will then write the disposition to the log, and then you get to have your good friend log rotation actually take care of getting the data back into your application. We've gone into countless companies that basically come to us and say, how do you handle log rotation? How do I do log rotation? How do I do parsing logs? And it's just people get so focused on the way they've done it for so long, they lose sight of what they're trying to do. Log rotation is a means to an end. It's a fine solution when that's the best you've got, but ultimately you're trying to get that message disposition data back in. So in terms of the problems with the approach, again, the application just needs to know everything about messaging. It used to be easier than it is today. It used to be you just make an RFC 2822 part, inject it, off you go. Now you've got authentication to worry about. You've got various other sorts of little markup things you need to do to the message, list on subscribe headers, all of those sorts of things you need to do to have your messages really be ready for mass disposition. And then more to the point, when you make a new application, whatever logic you have, you then have to replicate onto another system. Even if you make it modular, you still have this thing you need to maintain that's fundamentally auxiliary to your business. Again, messaging is an enabler for a business. Focusing on all of that messaging technology, it causes you to lose focus on what's actually making you money. And then aside from collecting the disposition information gets collected late with the log rotation strategy, no matter how sort of real time you do that. And as messaging has evolved, recipient management is incredibly important. Carriers actively measure how good a sender you are based on how quickly you respond to an invalid recipient response from them. So if you send a message to a carrier and they say, hey, this guy isn't here anymore, if you never send anything to them, send anything to that recipient, that's really good. If for the next week you keep on sending things to that recipient, that's bad. It shows that you're basically behaving like a spammer. So just looking at a scalable outbound message flow, the application just basically sends events, web events of some sort, into a messaging and policy engine, which then will send them which then sends them into a carrier. So this is made possible by having a modular policy engine within the messaging layer. So this is tied to all of the events that come in on an inbound SMTP connection. So a connection comes in, you're able to define connection policy there, and then the response goes back. And likewise, this goes back and forth with the EHLO phrase, mail from phase, recipient to phase. Then, of course, the recipient to phase can loop again because you can do multiple recipients. And then each one of these phases, you do the logical thing. In the connection phase, you could do some sort of logic based on who's talking to you because you only know the connection. At the mail from and the recipient to phase, you could do some checking to sanity check and make sure your application's sending in valid recipients. Alter those if you need to. Then once the message body comes in, then you have the entire system, the entire context of the conversation, so that you can really do some more advanced policy there, markup, authentication, and so forth. So all this the application needs to do is say, hey, here's this message I need to send. Go take care of it, and it does exactly that. So the message disposition information is once the message comes back, you need to do to get the information back in. With this policy, this ability to write custom code straight into the messaging layer, you'd think, great, I'll just write it straight back into my application. Well, what happens when that link goes down, right? Network goes down, application goes down. Happens all the time. It happens so often, in fact, that we decided that to follow the dictum of optimize for the failure path. So what we did is we created a library that we call JLog, just stands for journaled log, that's essentially a durable pipe. So the messaging engine writes everything into the JLog, which just sits on disk, and then there's a script that runs at the same time, pulling those things out. The latency of that is well under a second, so each event can go very quickly, but it could back up a week's worth of data if the application's down for a week. I hope it's not, but these things kind of happen, and that means you don't lose any data. We also open sourced it. It's, wow, I really should use bigger fonts. So that's labs.omniti.com/labs/jlog, if anybody's interested in that technology. That's something that we actually put out a while ago, but we've made a lot of use of it, and a lot of other companies have as well. So, second pass. Now we've got our modular message processing engine that makes handling the message intelligence go within the messaging platform and taking it out of the application. So the application just has to say, here's the business information, do the messaging stuff yourself. And the real-time durable message disposition information. We get all those events back really quickly. So the third pass is basically now we've got got the inbound and outbound, but we've got the outbound and we've got good introspection. Now we want to be able to handle inbound processing, handle these conversations. Talking about the Salesforce and the match cases earlier, this is where messaging processing coming in becomes very important. So, most people, again, you want to accomplish that. You use your good friend, the Unix pipe, right? So you have the SMTP server taking the reception in, and then writing through the pipe and out to the pipe handler, and then into the application. And then you know what's coming next. Lots more of that. So the problem with that is you've got some pretty significant abuse vectors there. Somebody can really hammer the heck out of it. And you need to be able to handle the sorts of inbound message abuse that happens. Talking about the SYN floods and things like that. Messaging has its own version of attacks. You do have the denial of service attacks. You have directory harvesting attacks. People going against an inbound server, trying to figure out what your users are. You have straight up spam you have to worry about. And again, same sorts of semantics that you have with a web application, just the messaging semantics. Also, you want to keep the inbound connection open while you're processing it. And the reason goes back to what we were talking about earlier with taking responsibility for a message. Until the message system, the MTA receives the message and then sends back the 250 OK after the data, the sending system still has responsibility for it. That sending system has logic for retries and things like that. As soon as you accept the message, you're responsible for getting that delivered. So you accept that message, and then you write it to disk, and you start to run it through your pipe. Then if there's something wrong with your pipe program, well, you still have to keep it, right? Something has to happen with that message. So the failure cases there get to be way more challenging. But if you're able to keep the session open while you're doing that, having that conversation, and then say, you know what? I'm not ready for that. Just send back a temporary failure. He'll say, great, no worries. I'll try again in 20 minutes. And that's really the way that whole system is designed to work. And then for all that to happen, the application needs to be tied directly in as opposed to through some sort of glue layer through a pipe. So processing at scale looks something like this. So as I said, you have the inbound reception, the application-specific APIs talk to the application in whatever REST API or whatever. Note the session's still open. So then we get the thumbs up, and then we send back the 250 OK, life is good. Then we get the thumbs down, that's no worries. We just send back a 451, and then he'll try again later. So that keeping the connection open just gives you a huge amount of flexibility. You just don't even have to worry about queuing any of those messages or any sort of retries because all of that happens outside of your walls. And one of the other things that comes along with this is you need to worry about abuse. Now, layered security is really the name of the game for security on the internet these days, and that's no different for messaging. So RBLs, real-time block lists, are really IP address filters. They're cheap. It costs some money to buy the list, but relatively speaking, it's cheap, both from getting the list perspective as well as the actual computational power. Our system can do huge numbers of these and not even break a sweat. Behavioral and heuristic filters. This is like, hey, this IP address has sent me 5,000 messages in the past minute, and I hadn't really ever seen any traffic before from him. That might be spam. I should shut him down, or I should slow him down for a little time, that sort of stuff. A little more expensive because you're using a little more memory for keeping that state, but still very cheap. And then when you're looking at the last line of defense is the content filter. Still need to have content filters because that's really the last line of defense. Those tend to be expensive, both primarily in terms of CPU, and then the commercial ones have their own cost as well. So visually, the funnel looks like this. You have the RBL, and this actually is not only a funnel in terms of cheapness, but it's also an effective representation of how much mail is caught. RBLs catch a huge amount of abusive traffic. Heuristics catch a little less, content scanners catch a little less, and then you're left with the clean traffic. So third pass, final pass, and then just a few more comments of where we're going beyond this, or where to go beyond this. Messaging layer is tightly integrated. The abusive traffic is blocked at the messaging layer, and inbound connections are kept open while the application is processing the data. All of that together yields a tightly integrated messaging environment with the application. It means the application can focus on what it's best at. So now we look at scaling horizontally. Tightly integrated messaging layer, so that's good. As volumes grow, now we really need to start to scale. We really need to mean business. And we look at multiple servers as well as massively multi-core hardware. So scaling messaging is actually pretty nice because each message is more or less autonomous. So scaling horizontally is not a lot that one message A needs to know about message B. In fact, it really doesn't need to know a lot at all. So intrinsically, messaging is actually very, very nice for scaling horizontally. But in terms of keeping track of statistics and those sorts of heuristics I was talking about, there's a lot to be gained by having a layer to do that. So the outbound delivery policy state in terms of really fine-tuning your delivery to deal with whatever sorts of policies the carriers are putting in, as well as any sort of policy you want to enforce of your own against messaging traffic that's coming in. So the traditional approach would be your central metric server that has a messaging node that's pushing data in, and then as each messaging node needs some data, well, then you go and try to pull the data out. I mean, there's obvious scaling problems here. There's obviously also the single point of failure problem. You can make two of them, but then you just have 2 points of failure, and you have all sorts of failure scenarios to work there. So what we've gone with is a peer-to-peer model for all of our cluster management. So what this means is that instead of sharing all the information into a central server and then querying it on demand, we actually share the appropriate information to all the servers on it when the event happens. So then what happens is that when that event goes out, every node has a picture of the entire cluster. So when it needs to ask a question, it's just looking at its local data structures and it's good to go. That approach has actually worked very well for us, and it's scaled extremely effectively. Even better when we start talking about some of the extra performance we're able to get out of the really massively vertically scaled hardware. So, final point is goes back to our overall architecture review. Remember, we have the single event loop, and we have these thread pools that are doing work. So servers in the 90s, when we wrote this software, you had a CPU. If you're really hot stuff, you had 2 CPUs, right? I mean, that was the state of the art. Moore's law was jacking up the clock speed at a really good clip, like doubling it every 2 years or whatever, and that meant that having everything in more or less having that one event loop that was doing stuff in a couple of worker threads, we were saturating the CPU, all the CPU in the box really easily. What we've got today, in theory, is you have that event loop running on one CPU, and you've got all these worker threads working on other CPUs. The problem is, in practice, the event loop's beating the hell out of that one CPU, but the worker threads just don't have a lot to do because there's so much network activity going on because the disks have gotten faster and faster and faster that those little non-blocking operations that happen in the event loop, all of those things start to add up. And that's when we ended up with our customers coming to us saying, hey, we've got this 16-core box, but we're only using 8% of the CPU. What's up with that? Well, what was up with that is that we decided to multi-thread our event loop. So basically, we created multiple event loops, and there were some challenges there. got a couple minutes, so I can talk a little bit about that. One of the biggest ones is that a lot of those data structures that I talked about that we created 15 years ago that were so clever were also entirely unthread safe. So the notion of just sharing them across the data structures across the threads was not really tenable. But what we were able to do is note that each of the connections was self-contained, and every domain itself actually was a container for its own mail queue. So we were able to federate those items on a given event loop and get some fantastic scalability. So that's how we've gotten to some absolutely insane levels of throughput, which has really gotten us to we haven't actually gotten to a point where we've hit a bottleneck yet, and I've got to talk to Archer and see if I can get to running on some of those servers, because I'd love to see what those could do. So that's where we are with that. Finally, scaling messaging, it looks an awful lot like scaling anything else. Minimize the use of slow and expensive resources. Maximize the use of anything that's fast. If there's something that's fast, use it as much as you can to take load off of the more expensive ones. Think really hard about the hot code paths. There's a ton of other stuff that we've done in some of our hot code paths around message parsing and things like that have gotten us some pretty significant gains. And set aggressive and realistic operating parameters. That's one of the things that we've learned the most from, is that we sometimes engineering gets operating in a vacuum, and it starts saying, oh, well, it works great under this scenario, but the scenario didn't actually reflect reality. Make sure that you have a good sense of what reality is when you're doing your scaling. And remember the cyclist Greg LeMond, it never gets easier, you just go faster. Thank you. Any questions? Eric.
Yeah, given what you were saying earlier about the relatively small number of really high volume destination domains.
Yeah.
And the way that you're splitting up your event loop across domains, do you find that you still have a problem of relatively few destinations that have really high volume can't actually spread that work out anymore, or have you figured out other ways to do it?
So the only part that would actually be that issue would be the actual mail queue maintenance, because the actual delivery, the actual action of receiving the message and delivery of the message actually has nothing to do with that specific domain. So we could spread those connections across all of them. We actually did implement a way for us to identify what those hot domains are, and then make sure that they are spread evenly across the event loops, so you don't have like Gmail and Yahoo and Facebook and Hotmail and anyway, all the big five living on one event loop, so that those get spread out. And then once you do that, then because at this point there's not enough mail queue activity that one of those is going to fully saturate a single event loop. Yeah.
Can you talk a little bit more about how you tune the sizing for the in-memory representation?
Sure. So. So tuning for in-memory utilization. So like, how do you figure out what's in the what to keep in memory? There are a lot of tricks we use there. Actually, the one thing, again, I probably do a whole other talk on some of the little things that we did. Slab memory allocators. Anybody not know what a slab memory allocator is? Read about it. It's basically they're fantastic for long-lived processes. They're basically essential, especially in this day and age. What it does is very quickly, instead of allocating memory wherever it can find it, you set up a slab memory, like a 4 meg block, where all you do is 2K allocations, and a 4K block where all you do is 4K allocations. That's a huge win for us. JE-malloc is what we're using now, which is freaking awesome. But that's not what you were asking. What you were asking was about how to pick what to use. So first of all, it's really just a math exercise. We figured that we didn't want to use about more than 60% of the RAM for our cached messages. So we basically just do a calculation based on how much RAM there is and say that's how many messages we keep in memory. We set up some parameters so that after a certain number of retries, we always drop the message out of memory. Because based on our statistical analysis, if you don't deliver a message in the first 2 tries, you're probably not going to deliver it. And that's configurable, but we tell our clients, if it's not gone in the first 2 tries, you might as well just fail it. You can keep on trying, but at least keep it out of memory so that the new messages can go through quickly. And those are really the two biggest things. Yeah.
With such large volume systems, With such large volume systems, I wonder how how autonomous your security measures are. Are your security measures in terms of the heuristics you talked about in your policies, are those self-modifying and adapting, meaning messages hit thresholds and then things kicking automatically, or is there a lot of babying you kind of have to do in the organization to keep those up to date so they don't miss newer types of floods and things like that?
Yeah, so if you measure your success in terms of no bad messages getting through, like you've already failed, because that's just unreasonable. So setting realistic expectations around what those should be is kind of the first step. The next step is to the heuristics are not going to protect you from everything. Right, the distributed denial of service attacks; those are the things like the spam house list, the spam house XBL, the SBL, and those sorts of things provide a huge benefit there. We found that defining classes of service is actually one of the most effective security mechanisms. So instead of just saying everybody gets 100 messages every 10 minutes, and then we basically, because most of our clients that implement these kinds of measures, they already have these kinds of databases of like known good customers, different classes of customers. So we work with them to map that onto a policy, and that tends to have it be basically working dynamically on its own. And the policy can be made it can be made as complex as you want. The standard ones that we do tend to be fairly static because every client is so different in terms, even our carrier clients, right? Like we have a cable company on the East Coast that has a policy that's wildly different from a mobile carrier that we use that's based elsewhere. And it has less, it's partially because you just have different people coming up with different ways of solving the same problem, but it's also just that they have different problems. Anybody else? Great, well, you get to go out 5 minutes and 30 seconds early to the break. Thanks a lot.